Welcome, everyone. We're just waiting a few minutes as people are joining the call. So, welcome. It's our second day today of the third Aspect User Forum. I'm Dr. Freya Gary, and I'm in the climate resilience team at the Met Office in the UK. Um, I'm co-leading with a colleague at the Barcelona Supercomputing Centre, the part of the Aspect project that's focused on developing prototype climate services with key users. And I'm here today to host this session with Dr. Bina Balansarangini, who's a member of the Predictability of Weather and Climate Group at the University of Oxford. Bina's co-developing aspects methodologies and connecting scientists with external users to enhance climate prediction applications. So as a quick reminder for anyone joining us for the first time today, the Aspects project seeks to advance Europe's capability to deliver actionable climate information to society by enhancing models, improving scientific and practical application in a range of different sectors. And we're particularly focused on seamless climate prediction, going from the next few months to a season through to the next 30 years. By integrating the state-of-the-art science and user-focused applications, Aspect is aiming to empower society to make better decisions around climate change and adaptation. So these Aspect user forums are annual events where we explore the latest seasonal-to-decadal prediction science and its real-world applications. It consists of 3 sessions dedicated to users and providers of climate services and other interested stakeholders. Today, we're on day 2. As a quick recap, yesterday on day 1, we explored the scope and benefits of climate predictions, and we provided an overview of how climate predictions are generated, interpreted, and applied across various sectors in the Aspect project. And we had a panel discussion sharing how predictions are being used in real world applications. One of our speakers yesterday was from the reinsurance sector. And I'm just going to share with you a quick advert for an event happening in June. And this is something happening in Leeds in the UK, and it's open to everyone to apply to be part of. So aspects are part of this project, and I'm going to share a little quick video about it now, which is just a minute long, which if I can.
Unlock the mysteries of tropical cyclones and their global impact in the finance sector. This year, we bring together the brightest minds to tackle one of the most pressing questions for the reinsurance industry. Be part of the future of climate risk assessment. Explore the power of data to unravel the past, present, and future of tropical cyclones. Discover how these insights can enhance financial resilience, helping reinsurers better prepare for and mitigate global risks. Are you ready to shape the future of climate risk analytics for the finance sector? Be part of the change. Be part of the solution. Be part of the hackathon.
So if that piques your interest, check out the link that my colleague from CMCC has shared in the chat, where you can find out much more information about the hackathon and apply to be part of it. And so that opportunity is open for the next 2 to 3 weeks. Right, so now I'm going to pass over to Bina to continue the session.
Hello, everyone. Today, we are excited to delve deeper into more discussion of technical advancements and how we might use predictions together with projections for societally relevant applications, helping you with decision making. First, we will have a keynote talk, then a panel discussion with 3 members of the Aspect Project. First, I want to give a warm welcome to Tim Palmer, who is a Royal Society Research Professor in Climate Physics and a Senior Fellow at the Oxford Martin Institute. His research focuses on weather and climate predictability, including extreme events. With a background in ensemble methods for forecasting uncertainty, he has contributed to multiple intergovernmental panels on climate change assessment reports and worked on projects related to climate variability and predictability. Tim was elected to the United States National Academy of Sciences in 2020, and his work spans both theoretical climate processes and practical applications such as malaria prediction, flood forecasting, and ensemble prediction methods. Tim did his PhD in Einstein's relativity theory and quantum physics, and he started his career in the UK Metaphys, and he's one of the 2 developers of the first ensemble prediction systems. And he continued his career at the European Centre for Medium Range Weather Forecast, leading the development of ensemble prediction systems using stochastic schemes. And Tim has recently published a book called The Primacy of Doubt. Those who are interested in understanding how the science of uncertainty help us predict and understand the chaotic world, please have a read. And today he's going to talk to us about the values, enhancement, and the role of artificial intelligence in climate prediction, including extreme events. Over to you, Tim.
Okay, thank you. Can you hear me okay?
Yes.
Super. I thought I would just talk rather than show slides, if that's okay. So my understanding is I should talk for 20 minutes, is that correct?
Yes.
Roughly? Okay. Well, tell me to shut up if I mean, one of the disadvantages of not showing slides is it's easy to lose track of time. So tell me if I'm getting close to the end, and I'll wrap up. Okay, so yeah, thank you for the invitation to talk. I was trying to kind of think about what I should talk about, and I think what I'd like to talk about is this issue about the interface between the basic science of climate prediction and the utility of climate predictions for decision making, because I think there are some subtle issues which still need exploring, in my view. Well, since Bina mentioned my book, The Primacy of Doubt, I do think that this notion of uncertainty is a kind of a linchpin to, well, it's a linchpin to most sciences that attempt to say something about the future. It doesn't really matter whether it's weather, climate, economic prediction, COVID predictions, conflict prediction. I mean, these are all predictions under under uncertainty. I mean, and considerable uncertainty. Some obviously more than others, particularly in the social sciences. There are the additional complications of how humans feed back on the predictions, which adds to the complications. But even forecasting weather and climate is a complex business. In some sense, ultimately, it's because the climate system is a chaotic, nonlinear system, which means, of course, that it can be the predictions can be sensitive to very small uncertainties in the starting conditions for a prediction. They can also be sensitive to exactly how the equations are coded into a model. So 2 models which might only differ by very small pieces of code can in turn lead to very large differences in their predictive capability. So something that I've been I suppose, worked on for much of my career is, moving away from the paradigm of, I don't know what you would say, 40 years ago or something, of thinking of the atmosphere or the climate system as a fairly deterministic system, to one that is much more probabilistic, and we do that through ensembles of forecasts. So I think ensemble forecasting is pretty much a kind of accepted technique today, although back, if you went back 40 years, it certainly wasn't. And there was a lot of debate about, whether it would be better to use computer time to somehow improve the model equations rather than, running the model many times in an ensemble mode. But these days, that debate has largely over. And of course, what ensembles do in the let's say for weather forecasting is that they give you a sense of when the atmosphere is in a very predictable state. In other words, when you can be confident about the predictions, or when it's in a very unpredictable state, a sort of more chaotic, unpredictable state, when the ensemble members diverge from each other diverge from each other very quickly. And so you have a prior estimate of that predictability, and that's proven to be very important for decision making. And I mean, a good example is in what's now called anticipatory action, which is basically when do the disaster relief agencies, humanitarian agencies, when should they try to send in relief, medicine, food, water, shelter, so on, to an area that is predicted to suffer an extreme event in the coming days, given that they have limited resources. And, the answer is that they can take now decisions based on whether the probability from the ensemble, whether the probability exceeds some threshold that they have predetermined. So that's certainly changed the way in which humanitarian agencies react to extreme weather, compared to, even 10 years ago. The aspect project is involved on longer timescales, perhaps, than weather, seasonal, multi-annual, decadal timescales. The basic kind of science behind that is that there are signals, or there are aspects of the climate system coming from the oceans, maybe coming from the land surface, to some extent, maybe even coming from sea ice and things like that, the cryosphere, which gives additional predictability to the atmosphere. So of course, the example that everyone knows is the El Nino event, probably the single most dominant mode of natural climate variability on the interannual timescale. El Nino, the warming of the central to eastern tropical Pacific, and that, of course, we know has substantial teleconnections to weather and climate around the globe. The Indian monsoon famously tends to be weak during a El Nino year, strong during a opposite La Nina year. But again, we need ensembles to really assess whether in any particular year and in any particular location we are seeing a predictable signal, a signal coming from whether it's El Nino or some other, could be the Indian Ocean dipole, or even some parts of the Atlantic. The signals from the oceans, are they producing a predictable impact on the atmosphere in the coming months or potentially years? Of course, on top of that, we have the problem of climate change, that we're gradually changing the CO2 concentrations in the atmosphere, and that also has an gradual impact year on year on the atmospheric circulations. But again, the way to address these is through ensemble forecasts. And again, the sort of bottom line here is that what an ensemble gives you is a probability or a likelihood, based on if you're interested in drought in some region of the world, then basically you would count the number of ensemble members that were predicting drought and the fraction of ensemble members predicting drought to the total ensemble size is giving you a kind of a measure of the probability of that drought. Now, just to say again, the ensembles are made by, first of all, well, there are two sources of uncertainty. One is the initial, if you like, the observations that go into creating the initial conditions for a forecast. These can be atmospheric initial conditions or ocean initial conditions, and of course, the subsurface of the oceans are, well, certainly better observed today than they were 20 or 30 years ago. But there are still big gaps in our observing system, particularly in the oceans and maybe even some areas of the atmosphere. So when we make ensembles, we have to obviously try to represent the uncertainty in the initial conditions. But also, as I mentioned, the models. I mean, the models are by themselves, the models are by their nature approximations of the true underlying fluid dynamic and thermodynamic equations. And typically, a model will discretize the atmosphere and the oceans into grid boxes. And the assumption is within the grid box, the atmosphere is kind of, and the ocean is homogeneous, and can be represented by somehow a simple formula. Well, of course, that's not true. I mean, the atmosphere is turbulent right down to the viscous scales virtually. So this notion that there's a scale where the atmosphere is, can I just hold on a second? Libby. Yeah.
Tim, you're muted. Tim, we can't hear you because you're muted, I think.
Oh, did I get muted again? Okay. We represent model uncertainty, well, typically for seasonal and longer timescale up to climate change. The primary method is to use what are called multi-model ensembles, and in a sense, this is a very pragmatic way of addressing model uncertainty. You just take the fact that different groups around the world have developed slightly different ways of representing the model equations, and one hopes that these models somehow span the range of uncertainty that exists. But actually, that's not the case, because as well as having, if you like, kind of random uncertainties, we know that models are biased. There are sort of systematic errors that models have when you compare them with observations. And the bottom line I'm getting at here is that we produce ensemble-based forecasts. I mean, the EU Copernicus, seasonal forecast system is a very good example of that, or the CMIP system for climate change. These are both multi-model systems, but we know that there are, and they produce probabilities, but we know that these, in some sense, these probabilities are not the last word in the matter. We want, we expect that models will improve in the future, well, not least, the resolution of the grid boxes or the size of the grid boxes will shrink as computers get more powerful, and that should help improve the accuracy of the models. So the point I'm trying to make here is that we we produce probabilities, but these shouldn't be considered somehow the last word in the matter. And in fact, there is a school of thought which says that the models actually are significantly underestimating the forced response to things like sea temperatures or land surface anomalies, and that in fact the probabilities, once we can properly represent this interaction between the ocean and the atmosphere, the probabilities will get much larger on the seasonal and perhaps multi-year timescales. On top of that, AI is now becoming a big player, and we're kind of waiting to see on the seasonal to interannual timescale how good these AI models are. And well, that's going to just be an interesting question. So the point I'm trying to make here is that the science is very much based on probabilities, but the probabilities we produce, the climate modeling community produce, should not be thought in some sense as the last word. Even when aspect is finished, there will still be work to do to improve the prediction systems. So what I want to do in the last just few minutes is turn the problem on its head, and I want to particularly address the users. And I want to pose the problem in a kind of inverse way, because I think this is important to kind of have a better dialogue, if you like, between the modeling community and the user community. So I'm going to make it just a very simple example, and I hope that if I give this example, you can, if you are a user that's that's potentially using these forecasts, you can kind of reframe it to your own particular needs. But I'm going to imagine that you are a farmer or maybe an agronomist that's advising farmers in a region or country or something. And the question is, what crop should the farmers be growing ahead of the rainy season? And just to make things very simple, perhaps there's two choices. One is if you like, a normal type of crop, which if there's plentiful rainfall, will produce a very good crop yield and make a lot of profit for the farmer, which is good. But if there was a drought, it could turn out to be a kind of a disaster because the crop might produce nothing. Or the other option is to plant a drought-resistant crop, but then there are two problems. The cost of seed might be considerably higher, and that if there was a normal amount of rainfall, the crop yield might be relatively small compared to the normal crop. Now, you see, this is the reason I'm mentioning this example is because if I told you that there was 100% certainty that there would be a drought in the coming rainy season or growing season, whatever, then there would be no doubt that the right thing to do would be to advise the farmers to plant the drought-resistant crop. Or conversely, if I told you there was a 0% chance of a drought, then obviously the correct advice would be to plant the normal crop, the seed would cost less, and you'd get a bigger return on the bigger yield and hence bigger profit. But the problem comes, what I'm trying to say here is that for seasonal forecasting, you will never, or virtually never, predict 0% or 100%. It's just the nature of the chaotic dynamics of the climate system that you just don't get these types of extremely sharp probabilities where every single ensemble member will say in the coming 3 to 6 months or whatever, there'll be a drought or zero rain or normal rain. You get an ensemble, and how much the ensemble kind of deviates from the climatological distribution of rainfall will depend on the particular sea temperature and maybe land surface, snow cover, various, let's say, land and ocean boundary conditions to the atmosphere. So what I want to do, what I want to just finish with, and I'll wrap up in 2 minutes, is to ask the users to think about this problem even before looking at the actual, let's call it aspect or whatever, Copernicus data. Just ask yourself this question: how sharp do the probabilities have to be in order for you to be able to use that information um, for advising, well, either yourself or for advising other users? So just to kind of make the point again, if I said there was a 100% chance of a drought, then for sure you would advise the farmers to grow the drought-resistant crop. If there was 90% probability of a drought, you probably also advise the farmers to plant the drought-resistant crop. But 80%, 70%, 60%, 50%. I mean, where you see, and again, it'll obviously depend on things like the cost of the seed, the drought-resistant seed, and the relative yield. All these factors will be important in determining, what is the threshold, uh, probability threshold, above which, let's say if we're talking about drought, above which, you can usefully use that information in advising farmers, or below which it's just too kind of close to climatology just not to be useful. Again, I would sort of come back to the example of the disaster relief agencies. They obviously don't have an infinite amount of money to spend on relief, and they can't afford for there to be lots of false alarms. On the other hand, they know if they waited for a prediction of 100% probability of an extreme event hitting a particular case, then they might never take action at all. So there's a kind of a calculation to be done based on, yeah, on what their resources are and the cost of taking action. There's a calculation which will say, well, okay, it makes sense to take precautionary action, anticipatory action when the probability of this extreme event exceeds, could be 80%, 75%, whatever it is, some threshold. And that's what I'm trying to ask the users to do, that type of calculation for their own applications, even without without using the actual forecast data, because then, you come to it with I think, a more realistic expectation rather than somehow expecting, we're going to get 100% probabilities and 0%. We know that's not the case. So if you've worked out a priori what can be a useful probability, and when that probability is just too close to climatology to be useful, if there's a 20% chance of a drought and you predict a 21% chance of a drought, then really there's nothing very useful about that forecast that you can't get from climatology. So that's what I want to, that's kind of my main point. I think I've running out of time now, so I'll stop now. But that's my point. I want to encourage a dialogue between the forecast users and the forecast providers, where the forecast users can actually think about these probabilities before they've even started to use the actual real forecasts. And then when the two groups do meet and come together, I think the discussions can be much more meaningful and useful. And for example, they can say, no, I'm sorry, at the moment your probabilities are just not sharp enough to be useful, but with a small improvement we can see something very useful and important. And that would be very big feedback, I think, to the modelers to try to get some investment to improve their forecast systems. So I hope that's Bina, I hope that's just fairly random thoughts on my part, but I hope that's a useful start for your discussions.
Yes, thank you very much, Tim, for the valuable insights into how users can contribute to reshaping the research questions scientists are facing and trying to deliver the climate information which can be usable and actionable.
That's great. Yeah, thank you. Okay, listen, I'm going to leave you because I have a few things to do. So is that okay?
I think we have just a comment from one of the users. If I can just read out to you, Tim, is
Yeah,
that
please.
all right? From Christophe Belperon, it's important to be able to work on multiple years with farmers. 1 year failure of prediction is devastating. 1 year failure of prediction out of 4 years with 3 years successful prediction is already much better. 75% success to build confidence on prediction.
Exactly. Yeah. No. Certainly, you can't make anything useful about just looking at 1 year. You have to look over multiple years and have a good. I mean, that's the other problem with probability forecasting. You do need a reasonably good sample size to know whether your probabilities are indeed reliable or not. So yeah,
Yeah.
has to be done
Before
over
you
multiple
go,
years.
thank you, Tim. Thank you very much, Tim. Before you go, can I ask just one quick question, a pressing one for the users probably. So what do you think are the current challenges and solutions? You definitely touched upon the relation between forecast sharpness and how one could use reliability diagrams, for example, to connect both these focus metrics and find the answers for the decisions. So what do you think are the critical strategies and challenges for users to contact the scientist and scientists to provide the answers to the users? Because especially with the advent of artificial intelligence and machine learning models, like what are your views whether traditional numerical weather predictions systems or together, both of them together, what would be like your insights for the future?
Well, I very much hope that AI will be used together with the physics-based models. And I think one of the most useful areas of application of AI is actually in going from the the model generated output, which is of things like, grid box temperatures and grid box rainfall, that sort of thing. And actually converting it into, I mean, in the example I mentioned, converting it into a crop yield, for example, tons per hectare or something like that. Because that's another obstacle to all of this is the amount of data that physics-based models produce, and it's terribly hard work for a user to kind of go into the data sets, analyze them, correct for biases, convert it to something that they find useful. And I think all of that can be done by AI. I mean, I hope in 10 years' time, a user will almost be able to use a model like ChatGPT. They would actually go in and say, I want to know, what I should be advising the farmers in region X or something like that. And the ChatGPT type AI would analyze the model output that would exist on the data on the various data servers, but convert that into a probabilistic forecast of crop yield for different crops, and that would make life so much easier, I think, for the users. So that to me is I think going to be more useful than just doing raw AI prediction. I mean, I'm not wholly enthusiastic about you doing AI prediction without any reference to the physics-based models. I think we're losing a lot of potential information there, and the big problem with AI is out of sample forecasts which isn't an issue with physics-based models. So I think there's a lot of stuff for AI, and I hope it'll make life for the user community much easier. It ought to. I mean, that should be a major goal, I think, of AI research.
Thank you very much, Tim. And thank you very much. Let's thank Tim once again.
Okay, it's a pleasure. See you all around sometime soon, no doubt.
Thank you.
Okay, bye for now.
So after we have heard the keynote speech, I think it's time for me to pass back to Freya to continue the next part of the session.
Thank you very much, Bina. We're really pleased now to invite a panel of 3 members of the Aspect project to talk about their work. Between them, they cover the science to services spectrum, including the creation and analysis of predictions, development of new techniques and methods, and climate service development. In fact, all of their work is contributing to one of our case studies in the Aspect project, which we briefly introduced yesterday, where scientists from across the project are working on methods to underpin development and design of a climate service prototype with the EU Mission for Adaptation, which is our governance sector key user. The mission adaptation is a European Horizon Europe programme focused on enhancing resilience to climate change by supporting regions and communities in their adaptation efforts. The case study is focusing on the Emilia-Romagna region of Italy. Of course, we know it's one of the most hazard-prone areas in Italy. And through engagement with the Regional Agency for the Prevention, Environment and Energy of Emilia-Romagna, Italy, the case study is being co-designed. So first on the panel, we're going to welcome Ralf Duscher, who's the head of Regional Climate Research at SMHI in Sweden. Ralph's interests are climate modelling, high-resolution climate models, extremes, and European and Arctic climate. So first, let's now invite Ralph to say a few words and share a few slides to start the discussion.
Yeah, thanks, Freya. I guess you can hear me?
I can, thank you.
Wait, I try to share. So, takes a few seconds to share. Okay.
That's just loaded for me now.
Okay, I guess you can see the presentation now. Good. Yeah, I'm going to talk about the new method. So we just heard from Tim about the value and usage of climate prediction, and that probability plays a role. Now we're focusing more on extreme weather in recent climate and in future climate. So climate prediction and also climate projection, longer terms of climate prediction, could be seasonal or could be tens of years, while climate projection cover longer periods until the end of the century, for example, 100 years long. But in any case, the basic climate information comes from a global model, because the climate, by definition, is a global problem. And if we want to know, if we want to learn more about what that means locally, then we need to downscale, which means we need to zoom in on certain localities, so that we can end up with resolutions of 1 kilometer, 2 kilometers, 3 kilometer, and do not stick with the coarse resolution of the global model, which is 50 to 100 kilometers. And Aspect has collected information about different downscaling methods, and those are published in an info sheet, which is available from the Aspect web page. When it comes to extremes, we really need this high resolution, which means kilometer scale. And here's an example from the Emilia-Romagna region. On the left-hand side, you see a global climate model, and the Emilia-Romagna region is indicated by red borders there. Then we can downscale it to 12 kilometer, which makes it a bit better. And then we go to 3 kilometer local model, and the colors indicate here precipitation. And this is the case where precipitation reached extreme levels. So just as an indication that downscaling actually gives us additional information which we would not gain from the global model, which could be the standard prediction model or projection model. Why is kilometer scale important? Why does it give us extra information? And this diagram is supposed to give you that information. So we were checking the output from a regional model over Scandinavia, and we were separating between Sweden, Norway, and Denmark, and the different bars you see in the diagram indicate the different versions of the model. And this is pink, you see the high resolution regional model, which is 3 kilometer resolution. And in gray, you see observational stations, and the other colors like blue indicate coarser resolution products. And we see that the kilometer scale, 3 kilometer pink here, and the gray bars observational station are close to each other. So there clearly is an added value so by increasing the resolution to kilometer scale, that clearly gives an added value, because the sub-daily return levels for extreme precipitation are captured here. And this is true for Denmark, Norway, and Sweden. And as an example, we're using here 20-year return period. So most extreme rainfall that occurs once every 20 years, for example. So there clearly is an added value in going to high resolution, which does not come by default from the prediction or protection models. So what do we learn from this? In order to assess local extremes, we need high resolution. The downside, this is very expensive computational-wise. We need the biggest computers that are available on national or even on European level. And the current workaround for us is to focus on a reduced number of extreme events only. So instead of simulating the climate 100 years ahead for all Europe, we are simulating only a limited number of events, which makes it computationally much more feasible. It actually can be done. An example is here. This is a real-life event from 2023, May, in the Emilia-Romagna region, with an extreme rainfall event. So in more practice, how is it going to work? The diagram on the left-hand side starts with the global model. We are scanning the ensembles, which Tim talked about earlier. So global models are typically run in ensemble mode. You run not only one realization, but you run several. And among all those ensemble members, for a certain region, we are searching for a certain type of event. For example, heat waves or extreme winds or extreme precipitation. So we are running a detection algorithm to find those events. Then the regional climate model will spin up, and finally we'll do the downscaling, which might be a day only or a week. But by running it only a day or a week, we save lots of computing time, which allows us to literally find and downscale hundreds of events for a certain region. So we do this for multiple events. We do that in recent climate and the future climate. And as the output of that, we can come up with the change of intensity, character, frequency of a certain type of extreme event in a certain region. We can skip that. Then, the expected outcome, as just mentioned. This is data-driven insights into how extremes are going to change for a certain region in terms of characteristics, intensity, frequency, duration. And during this project aspect, we were developing the method for Emilia-Romagna, and it will be applicable later in other regions as well. In parallel, we are also doing experimentation over Sweden, and we can literally downscale hundreds of events in recent climate and future climate. Yes, that's the work plan. So we will do an evaluation of the method based on reanalysis, so based on real climate. Then we will apply the method on recent climate for global climate protection and also for future climate. And in order to make the method even better, we need to continue discussions with the representatives of Emilia-Romagna, with the users. We started that discussion. and it needs to go on in order to finalize the shape of the output data. What kind of data is actually needed, and therefore it's important to know which events have the most significant impact in the region. Yes, that is what I had to say on this new method. Thanks.
Thank you very much, Ralph. That's a great introduction to this, a really important research methodology. As we know, extreme events have the most impact on society. It's what so many users are interested in. And we know the flooding that follows very intense precipitation is often what we see causing a lot of losses and damage across Europe. So next, we're going to welcome Dario Nicolai from CMCC. So Dario, if you want to start sharing your screen now, and I'll just introduce Dario a bit more. He's been working at the CMCC Foundation in Bologna, Italy since 2019 in the Climate Variability and Predictability Division. Dario's research focuses on decadal climate predictability and coupled modelling, particularly for the Euro-Mediterranean and the North Atlantic Ocean. He's contributed to the development of the CMCC decadal prediction system within the UKCP and Aspect projects. And since 2020, he's also been responsible for the operational production of decadal predictions. He's also involved in the Large Ensemble Single Forcing Model into Comparison project and the CMIP6 Decadal Climate Prediction project, contributing to the design, execution, and analysis of decadal prediction experiments. So I'll hand over to Dario to tell us more about exploring the potential of the 20-year predictions before we start the discussion. Just a reminder to drop in any questions into the Q&A tab as we go through, and then we will address them to the speakers afterwards. Go ahead, Dario.
Hello to everyone. Can you hear me? Can you see my screen?
Yes, all good. Thank you.
Okay. So, thank you for giving me the opportunity to give you a very brief overview about these explorative experiments that we are carrying on within the AFPET project, thanks to the contribution of our colleagues from WP1 and WP2 of AFPET. So we have already seen also yesterday the value of decadal prediction for climate services. Here we have just an example of the prototype climate services for the hydropower sector, a work led by Irini Zazzali in 2023, and we have seen that this the decadal prediction can fill the gap between the seasonal forecast and the climate projection. But now the question is if we can overcome this limit of 10 years and if there is any predictability beyond 10 years. So from literature, we are aware, for instance, on the left side, we have a work published by Harrell et al. In 2007, and they have found that there is predictable signals for the Atlantic Meridional Overtonian circulation, the EMOC, also beyond 10 years. And this is important because the EMOC drives decadal climate patterns not only limited to the North Atlantic region, but it also downstreamly teleconnected to the European temperature and precipitation. On the other side, we have a recent work published by Dusterus and Brun in which they have carry on this initialized 20 years experiment for their model, and they have found that there is still skill beyond 10 years for some key ocean basins, such as the North Atlantic or the Northeast Pacific, and again, the EMOC still play an important role in modulating this skill. So within the AFPET project, we are carrying on this multi-model initiative of initialized 20-year predictions. So on the left, you can see in the table the models involved in this exercise. It is worth to mention that this is an innovative and exploratory experiment framework, and the assessment is still ongoing. But from this exercise, there are several lessons to be learned regarding not only the hard skill and not only the skill beyond year 10, but we can also learn a lot about the behavior of the drift and the bias. And this can be useful also for the decadal prediction themselves. In particular, in this framework, we covered the period 1960 to 2025, and we initialize the system every 5 years. The simulations are 10 years long, and we have collected more than 70 members from initialized prediction and uninitialized simulation, which means historical and long-term projection to cover the period up to 2025. Here it is shown very first results. We have the boreal winter, so December to March surface temperature anomaly correlation coefficient, the ACC. The ACC is essentially a measure of the agreement, we can say, between the observed and the predicted anomalies. In these panels are shown the forecast year 16 to 20. This means that we hypothesizing we are looking at the prediction initialized in 2000, we want to predict the mean between 2016 and 2020 years. On the left side, we have the skill for the initialized prediction. On the middle panel shows the same for the historical, and the left side panel represents the difference among them. As you can see, we have found a ideal skill over the subpolar North Atlantic sea surface temperature, and this is important because that region is very well teleconnected to the European, to the wintertime European precipitation, but also to summertime surface temperature extremes. In particular, with this exercise, we want to bring the gap between the decadal prediction and the climate projection. Moreover, will be also a test bed for further development of climate model, not only also in the context of the seamless framework. And moreover, we also want to provide a more comprehensive and continuous link with the decision makers regarding the climate information. It is worth to mention that we are going to present a more comprehensive assessment of this exercise at the EGU within this section. And thank you.
Thank you very much. It's certainly really interesting to see those signs of predictability so far in the future, because it's a topic of debate in the community, isn't it? Where how useful this is. So it's fantastic to see. So for our third discussion, presentation, before we start the discussion, I should say, I'm going to invite Simone Taddeo to share your screen now while I introduce you. Simone holds a PhD in economics, statistics and sustainability, and is a postdoctoral researcher at CMCC, focusing on sustainability and climate finance. Please go ahead, Simone.
Thank you very much, Freya. Can you hear me well?
I can, yes. Thank you.
Thank you. Thank you very much. So for hosting me during this interesting panel session. And today I'm going to talk about the economic value of climate information to support decision-making process. So here, like we already mentioned, the benefit of seamless climate information in the decision-making context. So we already said how are superior to static models, since they provide some continuous integrated data across different time and spatial scales. So they enhance reliability and improve decision making and adapts dynamically using advanced modeling and big data. But just beyond their benefits, we must ask to ourselves, what are the true value? Are the climate information just a data or something more? In this I try to briefly show what are the difference between the value in terms of climate information in general and from the customer or alternatively user value. So we know that behind the practical benefits, the intrinsic value of climate information lies in its ability to empower society, so drive innovation and shape sustainable policies. So this may refer in a broader sense about all those environmental, social, and economic benefits. So all those practices that using climate-related data to prepare for risk reduction, economic efficiency, also long-term sustainability. Having said that, we also now introduce a new type of value. We know that the better we use the climate data and the better prepared we are for the future. But on the other hand, the value of climate information for customers, for users, aren't just about having access to data, but about how that data can directly improve the decision making and in turn efficiency and preparedness. So generally speaking, the user could be a range of stakeholders that goes from individual consumers or to large corporation and governance agencies. Here, the customer user value climate information is worth through its ability to make data actionable, so make the data relevant and accessible for decision makers across industries. We can say that this is, of course, context dependent. A strand of literature call this kind of value some actionable climate information. So those climate information that user can make upon to redirect outcomes or mitigate risks. There are some peculiarities in this kind of value proposed from users. So first of all, is just the relevance. So the tailoring the information to specific needs. So the value of climate data is significantly enhanced when it is tailored to meet specific needs of the user. So the climate information provided must align with the context in which the user is operating. From another hand, also acting in advance of climate events. So climate information in this context is bearable when it arrives early enough for the user to act on it. So timeliness gives the user as a competitive edge in preparing for extreme weather or adapting to long-term climate changes. And the most important thing, just turning data into decisions. So the true value of climate data can outcomes when it drives actionable decisions. What does it mean? This means that climate data is not just informative, but guides behavior. So whether that's changing farming practices, for example, or just like adjusting supply chains or taking some preventative action before a climate-related event. I just like wanted to show also like on the right table, like just some basic baseline scenario where it is essentially like a reference point used to evaluate the impact of improved climate information on decision making. So on the left box, we can see like this kind of baseline scenario, which decision makers often look at past events, so at historical climate data and past patterns to make their decisions. But at the same time, in a certain sense, they wait for the event to occur and then they adjust their action. And sometimes these often arrive at the costs that are more severe in terms of consequences. So just imagine like an improved scenario with action climate information, so integrated with this kind of climate predictive modeling with advanced climate modeling, probabilistic forecasts to bridge the gap between various climate predictions. So it empowers decision makers to act strategically rather than reactively, fostering like a more sustainable and prepared future. So where is like the value creation here? Where is like the value added? It falls like beyond like the differences. So the differences between the baseline scenario and the improved or how we say actionable climate information scenario represents the value added. This is also like already mentioned in a various trend of literature where the value added is also like conceived as the difference between the outcomes of a decision made with and without a forecast. So in other ways, just like comparing the outcomes among users without access to forecasts with the potential outcomes if they had like access to the forecast. Moving forward, this is just like summary of how is like the generated value from users, consumers. So we saw here in the first step that climate service production, there are employed different kind of steps before like the service delivery, and there are like also like employed some kind of climate modeling, some climate prediction and forecasting. But the true value here is like comes after. So the value of climate information from the users is not like in the data itself, but it is created through its effective use. So simply having climate forecasts or projections doesn't automatically lead to better outcomes. So the ability, the importance, like the ability to act on this information. Then assessing the value of using actionable climate information also employs a range of methods that span from quantitative and approach to qualitative approach. So these are just like a list of methods for economic valuation of climate information. I just like briefly describe like the contingent valuation, which are like measure how much like the people are willing to pay for better climate information or protection against climate risks. Other one is like the economic decision modeling, which uses just like data and forecast to predict the economic impact of climate of climate events, the avoided cost of analysis, which calculates the money saved by using climate information to prevent damage from disaster. And the other two are just like cost-benefit analysis, which compare the cost of climate action, like, for example, the early warnings, with the benefits. So, like, for example, fewer losses and better planning. And lastly, there's also like another kind of participatory methods and multi-criteria decision analysis that engage also like stakeholders to weigh different climate strategies based on multiple factors. So these kind of economic and qualitative strategy we are gonna employ in different SuperUser case studies that we have like in the aspect or package 4. We just like develop like a series of case studies that underline the importance of seamless climate information in decision making. So we just like span over different sectors. So from like the finance, in particular the pension sector, to agricultural, in particular the wine sector, but also to other kind of sectors, like, for example, as you mentioned, Freya, from governance, so European mission adaptation, and also looking also some strategies from like humanitarian health and migration, so we support like health of moving population. So this was just like a brief discussion about the economic value of climate information, and also in general how the customer play a key role in the decision process. And if you have like any questions, I really like to answer that. Thank you very much.
Thank you ever so much, Simone. That's really interesting discussion, introduction to a really important part of the climate service discussion, and it's something that is not necessarily often discussed in the sort of scientific only, discussion of the user needs, but it's actually something that is so important when we're actually taking these climate services and trying to make things useful for real world applications where economics is so important to everything. So it's really great to have this breadth across the science to services expertise in aspects and in this panel. So we'll hopefully invite all the panel now to put your cameras on, and please do share any questions in the chat, and for any of the panelists. So let's start with a question for Ralph. About extremes, as we've said, we know extremes are of key interest to users, and but what we also know from your, the harnessing value from prediction information around extremes is actually in very early stages, and often the methods that we're using for extremes that at the moment we tend to actually be using projection information and not predictions. So how might the prediction and projection community really help provide more useful near-term information on extremes in the future? What's your vision?
Yes, thanks, Freya, for the question. I think there are different ways, but, and some of them are connected to high resolution, which means small distance between different calculation points in our climate models. And there, within that topic, there are different ways to go. So one of the possible ways was explained some half an hour ago, which is using regional models, which we can afford in high resolution, and focusing them on extreme events only, and thereby limiting the computational resources that are limited. So we can run simulation of extreme events, how they look today and how they look in the future, and do statistics on the differences, and thereby assess how will extremes going to change in the future for certain regions. Another approach, also based on high resolution, is called Destination Earth, or digital twin of the Earth, which is an attempt to run a global model, or a small number of global models in kilometer scale resolution, almost in a way as we use climate models nowadays, so running 100 years and so on. And this is a project that gives a lot of hope, but there's also a lot of obstacles, and we are not yet there. So this is in the future. Then, of course, there is machine learning, and so the downscaling, going from the global scale to the local scale. This is methods based on machine learning are explored already today. And those methods rely on learning data. So we need to have climate data to teach those machine learning based algorithms. And those are partly coming still from classical climate models. So what I foresee for the future is a combination of these classic climate models in increasing resolution, or in increasing resolution for extreme events only, and a combination with machine learning based methods. So maybe I guess that within the next years, dare to say within the next 5 years, we will see an improvement in the assessment of extremes.
Thanks, Ralph. We've got a question in the come in from the audience now, so let's move to that. We've got a question here, I think, for probably for Simone, but feel free if anyone else wants to comment as well. The question is, for the economic value assessment of actionable climate information, how would you account for the quality of the climate services, and how would you define the quality in such a context? So that's a very good question.
That's really a good
Simone,
question. That's really a good question. Yeah, like the quality of the climate services, of course, like it's like an important factor that help us like to make like really reliable decisions on this, but also like the quality like has like different kind of standard to be like measure. How can you evaluate like a climate service in such like quality? So I think like this is like an important discussion that needs to be dig in more inside of that. But I saw another like okay, so like about like the quality in such a contest, it depends also like on also like in sector that you rely on, which kind of like sectors you need like to rely on short-term decisions, also like in the management of immediate risk. For example, if you the quality can be more employable in a short-term decision rather than the long-term in some ways, but also happen the other way around. So it is really dependent on the context.
thanks very much. Let's move to a question for Dario now. So we know users are particularly concerned with extreme heat and intense rainfall that happens locally or regionally. So we have a question here about skill, about how, based on research, do we know if there's skill or reliability in predicting these extremes more regionally in Europe? And related to that, you know, we know how we communicate skill is also really important. And do you have some thoughts on how we can communicate skill transparently, or how might that be done better?
Two critical questions, I mean. So regarding the question about the extremes in the future, I think that this is the challenge. This is the challenge. Assess the reliability of the occurrence of these extremes at a regional level in Europe. We are aware that from the prediction side, I would say, we are able to we have also the additional information of the initial condition within the prediction that help us to better assess the extremes. There are several works also carry on in AFPET on this, but beyond the 10-year time pressure, we can say that we have we're still working on this. Regarding the transparency that you mentioned, regarding the second question that you have raised, I would say that we should develop to communicate with the user in a transparent way. It is essential to have visual communication tools which are intuitive, such as the one mentioned yesterday from the WD, the traffic light system. But we are also to regionalize the skill information for the users, because many users can be interested in general to close not at global scale, for instance, or just Europe, but maybe to the, as I mentioned, the river catchment areas for the hydropower sector industry. And yes, but last but not least, we need also the feedback from the users, because we can communicate in transparent way if they feedback us how we are communicating at the end.
Thanks, Dario. Maybe we've got a question from the users, which maybe I'll address to Ralph here. We've got a question asking, is there evidence that extreme events are changing more greatly, or is there more change in extreme events compared with how much we know the climate mean is changing?
I'm not sure if I fully understood the
I
question.
think
What evidence do we have that extremes are actually changing?
Yeah, and are they changing? Is the change more significant than we see than in the sort of the mean climate state? So I think yeah, my interpretation of that is that you know, we're certainly seeing more instances of extremes, and they're becoming more frequent, but they're also more intense. So obviously, with the climate mean change, by definition of a mean, you don't see that intensity, which is really and frequency. I mean, so they're quite different metrics, aren't they, Ralph?
Yes. So what we know is quite limited. So by physical laws, we understand that from if climate becomes warmer, then we expect more precipitation. According to physical law called Clausius-Clapeyron. Then the question is, how is this distributed? Is this distributed evenly? And there is recent research that tells us it's not distributed evenly, but we expect extreme precipitation that exceeds this physical law, but only very locally. So the distribution within a regional area can be very local, which leads to extreme precipitation. So then if we look for studies, how did it actually change? And so my own area here in Sweden, we have so far difficulty seeing that it has already changed. So we can see a change, but it's not statistically significant yet. But from climate scenarios, we clearly see that it will increase. And I'm not fully up to date with respect to other regions.
Thanks, Ralph. That's great. So thank you very much to our panel. We're going to close the discussion there and move on to the final 10 minutes of the session where we have another interactive activity which we hope you'll join us in. So I'm going to pass over to Bina now to introduce this final section.
Thank you, Freya and panelists, for this interesting discussion ongoing. Now, we would like to invite the audience to join us in an interactive session using Mentimeter. If you haven't seen this before or heard about it, just go to www.menti.com website and enter the code 33424902, or you can look at the QR code displayed. We just have a few short questions. This is really useful for us to hear about your perspectives and experiences using climate prediction information and how we can help you by providing more useful and usable science and services in the future. So if you could press some likes, we can know how many of you are already on to menti.com. That's good. Thank you. Let's move to the first question. What is the biggest barrier to applying climate predictions in research or operational settings?
I think that might be the second question. I think we have another one first.
Sorry. I'm not on Mentimeter. Okay, sorry, I couldn't.
It's okay. I've got so which aspect of climate prediction research interests you the most?
Most, yes, yeah, thank you. Yeah. That's great. So we have 9 responses favoring user-driven co-design and operational implementation, and just followed by visualization and communication of predictions. Let's move to the second question. What is the biggest barrier to applying climate predictions in research or operational settings? Yes, we have been covering the theme, which is the answer as well from the audience. That's really encouraging to know that uncertainty and model biases dominate the biggest barrier, followed by limited collaboration between researchers and end users. Yes, thank you for joining us here, because aspect is what the collaboration between researchers and end users. And we also have some computational or technical limitations. Yeah, thank you. Let's move to the next question. How can aspect better support users in applying climate predictions. Quite related to the example which Tim Palmer was explaining to us at the end of his talk. Providing a more reliable state of future hydroclimatic variables. Making daily data from past and future predictions easily accessible. Help users interpret the forecast and the uncertainty. Providing user-relevant metrics, user stories, use cases, specific training and dissemination of how to apply predictions, organize training on using long-term predictions, offering training and resources to interpret and apply predictions effectively that would enhance user engagement, provide guidance around uncertainty and limitations. We can wait for a couple more seconds if anyone is typing more responses. User base should be expanded in order to get diverse requirements. Thank you so much for all these enlightening points and suggestions. Yes, I think we have one more. I'm not able to see that. If somebody could read that. I think it's time for me to pass back to Freya for continuing and wrapping up the session. Thank you so much for all your valuable suggestions on improving the interaction of aspect scientists with users. Thank you, Freya.
Thanks. Do please continue to fill in the Menti on this last question about how useful you found the session today. That's really useful for us to know. I apologize if you can't see me. My camera has maybe decided to not work for a bit now, but you'll be able to see Bina instead. So thank you very much for coming today. Tomorrow we're really excited to hear from more users of climate information. We've designed the third session of the user forum as a matchmaking platform. So we're going to connect those in need of specialist climate predictions with experts developing cutting edge solutions. Open to all, the session consists of 2 panels. The first will showcase existing applications and services from climate prediction providers, while the second will highlight user perspectives, exploring real-world needs and challenges in applying climate predictions. This interactive format helps to foster dialogue, facilitate collaboration, and bridge this gap between supply and demand in the evolving climate service marketplace. Some of the organisations being represented tomorrow include ECMWF, who are helping provide all the aspect simulations so you can access them, AXA Climate, Technalia, Amigo, SRL, the Climate Data Factory, the Climax Project, and Region Bagster by Stricker. So we look forward to seeing you tomorrow. Thanks again for coming. Thanks to Tim Palmer for the provoking keynote today, and our Aspect panel of scientists for presenting and discussing their work. Thanks to CMCC, of course, for organising and hosting the user forum. Thanks to Bina for co-hosting with me, and thank you for your questions and joining us today. Goodbye and have a great rest of the day.